Welcome to the lecture on input energy and dissipation of the energy due to viscous damping in a single degree of freedom forced vibration system. So we know that in a spring mass damper system we have these three elements. When we apply a force on this system, we give the energy input in the system. If we don't apply the force and we disturb the system due to the damping, the vibration will be damp out, the system will come to rest. It means that to maintain its motion we need to provide the energy through application of the external force, because in each cycle there is the dissipation of the energy in the damper, because damper is the element that dissipates the energy. So today we have to discuss that how much energy is given to a single degree of freedom system when there is some harmonic force applied to the system, like F equal to F0 sin omega t. So if this force is applied on the system, how much energy per cycle is going into the system, and then we will try to find out that how much energy is being dissipated in the system, mainly due to the damper element. So let's discuss this. So we take a single degree of freedom system. So we have this system, and this system is subjected to some force F0 sin omega t. So it is a harmonic force the system is subjected. So we have F equal to F0 sin omega t. Now we know that due to the effect of this force, the response of the system will be also harmonic, but with some phase lag phi. We are talking here about the steady state response. So here x equal to x, let's okay, so x sin omega t minus phi. So this is x. Now if we want to know the energy input to the system, per cycle. So what is the energy? Energy is nothing but the work that this force will do to move certain displacement of this system. So if we say, let's say elementary energy dW equal to, let's say, F into dx. So if we want to know the energy input per cycle, so here we can write F into dx by dt into dt. So that is nothing but F into x dot into dt. So here if we want to know energy, so that is the work done. So for one cycle we say 0 to 2 pi upon omega, because 0 to time period and time period is 2 pi by omega, and dw so equal to 0 to 2 pi by omega f into x dot into dt. So here we can write, so f equal to f0 sine omega t and x dot we can find from here, x dot, so it is omega into x into cos omega t minus phi. We differentiate x with respect to time t, so x dot equal to omega x cos omega t minus phi. We can write it omega x cos omega t minus phi into dt, and this is 0 to 2 pi by omega. So here we can write f0 into omega into x 0 to 2 pi by omega sine omega t into cos omega t minus phi dt. So now we have to solve this integral, and we know this formula that 2 sine a cos b equal to sine a plus b plus sine a minus b. So this is the formula that we can apply here. So we can write f0 omega x by 2. So when we divide 2 multiply 2, so this is 2 sine a cos b. So we can write, so sine a plus b, so it is 2 omega t plus omega t minus phi, 2 omega t minus phi plus sine a minus b, so omega t minus omega t plus phi. So it is sine phi into dt. So this we can do f0 omega x by 2. So here sine theta, so we have cos 2 omega t minus phi and we are integrating, so we will have 0.2 omega, and this limit 0 to 2 pi by omega plus sine phi. So this will have sine phi into t, and this will have the limit 0 to 2 pi by omega. So f0 omega x by 2 into, so here we have, when we will have 2 pi by omega, so it will be 4 pi cos 4 pi minus phi. So cos 4 pi minus phi will be cos phi minus when we have t equal to 0, it is cos minus phi. So cos minus phi is again cos phi upon 2 omega plus here sin phi into 2 pi, t is 2 pi by omega, so 2 pi by omega minus 0, so it is. Now this is this term will be 0, this is 0. So we will have energy input per cycle equal to f0 omega x by 2 into 2 pi by omega into sin phi. So we will have omega cancel out, 2 here cancel out, we will get pi f0 x sin phi. So this is the energy input per cycle in a system, single degree of freedom system, that is subjected to some harmonic force. Now we take some cases here. So if we remember the vector diagram that we made for the forced harmonic vibration of a single degree of freedom system, so we have this vector diagram. So here this is x and this was f0, then this is kx, this is c omega x, and this is m omega square x, and this is phi. So if we see when omega is much less than omega n, the phi is very small, and in this case so omega is very less, so the inertia force m omega square x is the inertia force, that will be negligible or very small, even this force will be smaller. So the mainly the applied force is mainly balancing the spring force. However, when we come to the resonance condition, in the resonance condition when omega equal to omega n, so let's take the resonance condition. So this is x. Now in case of resonance, as we remember, the phase angle is 90 degree, means the angle phi that is between x and f is 90 degrees. So this is x, and here this is my f0, and this angle phi equal to 90 degree. Then this is spring force kx, this is damping force c omega x, and this is the inertia force, that is m omega square x. So here phi equal to 90. So in the resonance condition, we see that spring force Kx is equal to m omega square x. So this means that omega equal to root k by m, and that is nothing but omega n. This is what is the resonance condition, that is omega equal to omega n. So that is satisfied. Again the F0 is equal to c omega x, means the applied force is balanced by the damping force. And so the x equal to F0 upon c omega, and we can write F0 by k c omega by k, and that is nothing but F0 by k is the static zero frequency deflection, and c omega by k it is 2 zeta into r. R is omega by omega n, and that is 1 for the when omega equal to omega n. So the resonance amplitude is inversely proportional to the damping. Okay, so the energy dissipated per unit per cycle. So of course this is energy dissipated by the damping force c omega x. So if in this formula we put here, in spite of F0 I put c omega x, so I can put pi and c omega x, because this is a damping force. I want to know the energy dissipated by the damping force, so I put the, in spite of F0 I put c omega x, or this, into x into sine phi. So sine phi is minus 90 degree, because c omega x makes minus 90 degree angle from the x, so it is minus 90 degree. So this is minus pi c omega x square, because sine 90 is 1 and this minus is here. So it only shows that energy is dissipated. So energy dissipated by viscous damping in one cycle equal to pi c omega x square. Second. Okay. Now energy input at resonance equal to, if we put phi equal to 90, so it will be pi f0 x. Now if we make a plot of the energy or work done, and here so if we have x here, so one line is like this is energy input that is pi f0 x, so it is a straight line, while the energy dissipated here it is per cycle, that is parabolic, so it is like this, so it is, so this is pi c omega x square, so energy dissipated, this is energy dissipated. So here we see that the of course energy input should be is greater than energy dissipated, because not all the energy is getting dissipated, some energy is used by the system to for its vibration, and there is the conversion of the kinetic energy and potential energy interchange or interconversion between potential energy of the spring and the kinetic energy of the mass. Now we can take one example, one numerical example. So here we have to determine the power required to vibrate a spring mass dash part system with an amplitude of 1.5 centimeter and at a frequency of 100 Hertz. The system has a damping factor of 0.05 and a damped natural frequency of 22 Hertz as found out from the vibration record. The mass of the system is 0.5 kg. So we have a system, so this is our spring dash part mass system, so this is our system. So here mass is given 0.5 kg. We need to determine the power required. So power means the energy per unit time that is required to this system. So this system vibrates with amplitude of 1.5 centimeter. So here x is 1.5 centimeter, that is 0.015 meter, and at a frequency of 100 Hertz. So here omega equal to 2 pi into f. So here 2 pi into f is 100 Hertz. So it is 200 pi radian per second. So here now the system has a damping factor of 0.05. So here the zeta is 0.05 and a damped natural frequency of 22 Hertz. So omega d, that is the damped natural frequency, that is equal to 2 pi into 22 hertz. So 22, so that is equal to 44 pi radian per second, because we are converting this hertz to radian per second. Okay, so we are giving these data and we have to find out the that what is the power required. So because the power required per cycle will be the power dissipated, and to get the power dissipated, first we have to find the energy per cycle, energy dissipated per cycle. So energy dissipated per cycle, so what is the energy dissipated per cycle? So energy dissipated per cycle, because this is a viscous damping, so we just derived the expression energy dissipated per cycle equal to pi c omega x square. Here we know omega, we know x, we have to find the c. C is the damping of this system. So to get the damping, so here we have the omega d. So omega d is equal to omega n root 1 minus zeta square. So damped natural frequency is root 1 minus zeta square into omega n. So this implies that, so omega n root 1 minus zeta is 0.05, 0.05 square. So when so equal to omega n into, if we solve this, this is about 0.999. So we can assume that omega d equal to omega n, because this quantity is this 0.05 very small, and this is almost equal to 1.99. So we assume omega d equal to omega n, and omega d we know, and omega n. So now if we want to know the damping c, so c, we know that zeta equal to c by cc, and cc equal to 2m into omega n, or 2 root km. So from here we can find c equal to 2m omega n into zeta. So 2 into m is 0.5, and omega n equal to omega d, that is 44 pi into zeta, zeta is 0.05. So we can get c c. So it is 6.91. So now we get c, now we can get the energy dissipated per cycle. So Ed per cycle equal to pi c omega x square. So equal to pi into c, that is 6.91 into omega, omega is 200 pi into x, x is 0.015 square. That is, we can calculate that is 3.07. So it is 3.07. So now this is energy dissipated per cycle. So we need the energy dissipated per unit time or per second. So energy dissipated per second is energy dissipated per cycle into the frequency. So because frequency is number of cycles per second, so we multiply, so 3.07 into here frequency is 100 hertz, so we multiply with 100 and we get 307 watts. So this is in watts, and this will be equal to the power requirement. So this is the power required for this system. Okay, so we stop here, and thank you for attending this lecture, and let's meet in the next lecture. Thank you.